Well, good morning, everyone. It's a great pleasure to be here, and thank you to the organisers for inviting me to this very excellent conference. I'd like to give you a flavour of some of the things that we're interested in when we study AGN, and in particular as we move into the LSST era. The UK has just joined the LSST consortium as a country. So the government is investigating £18 million to allow 100 principal investigators across the country, so across all of the UK universities, to join LSST. And with that, each PI can have their postdocs and students. So in principle, that will be 400 UK scientists who have joined LSST this year. I lead the AGN Science Working Group, and the interests in the UK are actually very broad. We have a very strong high redshift community who have significant amounts of ancillary data. They've been doing surveys for many years, particularly in the optical and the infrared, and they're now moving into wavebands like the sub-parsec. We also have a very thriving time domain community, and I'll show you some of the work that we've been doing on high energy sources, particularly blazars, but also lessons that we can learn from the gamma ray burst community, which is a community that I work actively in, and how we put all of those together in the LSST era. And of course, AGNs sit in galaxies, and so we then interface with the Galaxy Working Group, and also the low surface brightness kind of technology side of things as well. And so to give you a size scale of what we're talking about for AGN, obviously the active galactic nucleus itself refers to the accreting supermassive black hole at the centre of the galaxy. The accretion disk we think of on Taylor scales of astronomical units, so it's a very small scale but high energy accretion region. We don't yet have direct images of the accretion disk, and obviously that is most likely to be obscured in many of the LSST AGNs. The accretion disk produces the ultraviolet and the X-ray radiation, and in fact, in many cases, is the defining characteristic of AGN. Going further out, we have obscuring dust and gas, called this the obscuring torus. It depends who you speak to as to what size scales this is on. Some people think of it as parsecs, some think of it as hundreds of parsecs, and in fact, these are continuous gaseous structures from the inner regions of the host galaxy down to the accretion disk. The inner 1 kiloparsec, we think, is the key region within the galaxy that is important for the AGN, because inside this 1 kiloparsec is where the dynamical timescales of the host galaxy gas start to become comparable to the activity timescales of the accreting black hole. And so that's the region where much of our spectroscopic and imaging spectroscopic efforts are now going, particularly in the era of ALMA. And then, of course, as we go out into the larger scale of the host galaxy, host galaxies can reach up to hundreds of kiloparsecs. And so the question is, can we look for dynamical triggers and environmental effects at the very largest scales, and potentially the faintest structures, to try to understand what's triggering and fueling the black hole 6 orders of magnitude down in size scale. And I think there were some questions yesterday about the timescales of triggering and what we can see in LSST images and how we might study cause and effect. So we have actually detected accretion disks, and in fact kinematics are a very important tracer. This is an artist's impression of a spinning disk, and if we only look at Newtonian dynamics, you get the classical 2-horn velocity profile that people who study hydrogen and galaxies will be very familiar with, this top panel here. If we then add in special relativity, you get Doppler boosting of the side of the disk that's coming towards the observer, and that gives you the asymmetry in the 2-horn profile. And then if we add in gravitational redshift to the photons, we actually get a stretching in red room, and that's what then gives you the bottom panel profile. And this is a very classic accretion disk profile for highly spinning disks. And the first observational proof that this was the case came from Tanner et al. In 1995 in the X-rays. So this is a very nice experiment at the FEK alpha line, showing that we have spinning accretion disks at the centers of galaxies. And the inner edge of the accretion disk tests the black hole spin. The first direct measurement of black hole mass came in the radio. This is Lincoln Greenhill's team again in 1995, and they were studying the nearby galaxy NGC 4258. And the center of this galaxy has water megamasers in the accretion disk. And this is a very nice conspiracy, if you like, that we have a neutron galaxy with dense molecular gas clouds. They looked at the maser emission at 22 gigahertz, and you can see the spectrum down to the bottom. You can see the central lines, which are basically the systemic velocity of the galaxy, and then you see the high velocity lines blue and redshifted. And I think this is still the case. This is the fastest known spinning disk in the universe. It's 1,000 kilometers per second. And they were able to measure the central black hole mass, 40 solar masses within less than the central lightning. So this was the first direct proof that a black hole exists at the center of the galaxy. But of course, we have one at the center of our own Milky Way. These are painstaking infrared observations taken by a German team and also a US team. You can see the dates in the top left-hand corner. And if I run the movie, you can see the stars around the center of the Milky Way. There's a star that whips around where we think the black hole is, which is marked by the yellow cross. And if we zoom into this movie, we can actually track the path of the stars over the course of a decade and a half. And in fact, that kinematic structure gives us the black hole mass, a few times 10 to the 6 solar masses. Or as I sometimes say in popular talks, 15 billion suns per cubic light. There's nothing else that could be a part of a black hole. And of course, we now think that black holes are implicated in galaxy formation and evolution. When I was doing my PhD, I was actually working on host galaxies of AGN, and I would go to AGN conferences and people only cared about the accretion disk there. And then I would go to galaxy conferences and all the people there threw the AGN out of their galaxy samples because they considered them to be a nuisance and an aberration. And of course, the revolution came in 1998 when we realized that all bulge-dominated galaxies contain supermassive black holes. We don't know which comes first, whether the black hole seeds the galaxy or whether the galaxy collapses and forms a black hole. The idea is probably that population 3 stars, the first population of stars in the universe, maybe produce 10 to the 5 solar mass black hole seeds, and those black holes then can actually gather the galaxies around them. But the well-known black hole bulge correlation, which is shown here now in terms of black hole bulge, this is actually the magnitude of the bulge and also the velocity dispersion, which gives us a tighter correlation. This holds for AGN, and it also holds for normal galaxies. And there's much work being done at the moment observationally and theoretically to understand what the actual slope of that correlation is and whether it still holds at the highest mass black holes. We know that 10 to the 10 solar mass black holes are somehow fallen early on in the universe, and we don't know how to produce them because there isn't enough cosmic epoch to grow them. And much of the current work now is actually looking in more detail at this correlation to understand whether it really is fundamental and it's telling us something about the galaxy evolution processes. And in fact, it's been found for the local universe that there are selection biases. Obviously, in order to be able to measure the mass of the black hole accurately, you actually have to resolve the sphere of influence of that black hole. And it's being shown now that that bulge, black hole bulge mass correlation may be biased to the high side, and in particular the AGN masses are over-biased. This is work by Francesco Cianca and his group, and they've been looking at this bias. And the idea is that actually by overestimating the mass of the black holes in the AGN, our whole correlation is then higher than it should be. And this, of course, causes us problems because if we don't correct for that, then we're overestimating black hole densities in the universe. If we correct for that, we may actually then have to increase the radiating efficiencies, and therefore the black hole spins also get increased. And the Milky Way sits down there. We also are starting to discover that AGN have very episodic activity. And this might sound obvious to those of you who are not in the field. Original calculations by the likes of Soltan in 1982 assumed a quasar lifetime, 10 to the 7 or 10 to the 8 years. It added up all of the mass in the universe and then distributed what was needed in black holes based on that activity accretion lifetime. But we now realise that actually AGNs switch on and off, and this will be very important in the LSST era, given that we'll be probing down to such faint magnitudes. We showed back in 2010 in a nearby galaxy called NGC 4151, which is a classical Cepheid type galaxy. It's a large, grand design barred spiral, and it has an active nucleus. And we actually found a 3 kiloparsec halo of soft X-ray emitting gas that filled the central hydrogen bubble. So you can see in red here, this is the H1. In yellow, this is these H2 regions producing H-alpha emission. And in the centre is the AGN and a significant amount of ionized gas being produced due to the ultraviolet photons from the accretion disk. And actually filling this H1 hole in the centre is the extended X-ray emission. And when we did the calculations of the mechanical energy deposition and the pressures in the gases, we actually had to conclude that this fairly normal Cepheid galaxy in the local universe was accreting at the Eddington rate just 10 to 25,000 years ago, which is really very recent. And this, of course, completely changes our ideas of the kinds of life cycles of AGN. We now also know that the Milky Way has the famous Fermi bubble. These are 50,000 light-year bubbles stretching above and below the Milky Way disk. These are high-energy particles that are emitting the gamma rays and the X-rays, and we don't yet know how to accelerate those particles. These are clearly not relic loads left over from some previous epoch of activity at the centre of our Milky Way. We don't see a very active nucleus at the centre of the Milky Way, but we see particle acceleration. So it's clear that that episodic nature of AGN lifetime is important. And that then changes the kinds of accretion physics that we have statistically across the universe. The other thing that has been happening in this field is actually the explosion of kinematic data that's been available. So if you care about luminosity functions, you might take a single long slit. SDSS, of course, has been revolutionary in this, so you can just go in and mine the data. You can take out the multi-band photometry, you can take out spectrum, you can do emission line ratios. It's literally as easy as that. And we did this for 360,000 active and inactive galaxies selected from the SDSS. We were originally trying to understand whether AGN that live in the so-called Green Valley, that live between blue active galaxies and red and dead host galaxies, whether they were actually an evolutionary transition population. And what we found was this was not the case. They were not actually in the process of building stellar mass. They had just accreted some external gas and had an instantaneous burst of star formation, which then explained their green colours. But we also found that these sorts of AGN host galaxies favored less dense environments and so were less likely to be found in galaxy clusters. So we wanted to understand the mechanism that underpinned these statistics. And so we used the 6.5 meter Magellan telescope in Chile to actually take a subsample of active and inactive galaxies matched exactly. So they were all selected on black hole mass. There was no bias in terms of, as far as we could tell, in terms of the host galaxies. And we then wanted to look at these host galaxies to see if there was a difference between them that would tell us why half of them were active and the other half were not. And this just shows you the selection criteria. So we control the redshift, absolute magnitude, which should the bulge mass, which is therefore black hole mass, also inclination, and the extent of the galaxies. So try to control all of that, including environment. And hopefully, if we've done our job well, nobody will be able to tell the difference between the active and the inactives here. We have them paired up, and nothing should stand out. Unless I show you the spectrum, there should be nothing that shows you which has an active nucleus and which doesn't. And what we were most interested in was actually studying the kinematics of the stars and the gas. This is the field of view of the IMAX IFU, much smaller than anything obviously we'll be covering in LSST. If I now show you typical spectrum, it's a very nice instrument because it has a very large spectral regime. This is just the stellar continuum. The flickering is the noise in each channel, and we're actually moving along the spectrum here as a function of wavelength. And at some point we will come to the first nitrogen line in the spectrum, and you'll see it's typical of a rotating disk because it will move from here to here, just like that. There's the hydrogen, there's the second nitrogen line, very, very bright gas. And we have exquisite spectral resolution as well. As we move along here, we'll also reach the two sulfur lines, which again we can measure the two-dimensional imaging velocity field. And of course the spectrum goes all the way down here to O3 and HP, so we have a number of atomic transitions in the spectrum. So what that lets you do is it lets you extract the distribution of the gas in all of these different transitions, and it also lets you extract all of the kinematic information as a function of position. And this is just one galaxy. You can see the distribution of stars, the velocity of the stars, the velocity distribution. Similarly to the hydrogen alpha gas, which when we look at the line ratios is actually star forming. This is not ionized by the AGN. This is actually star formation in the disk. And similarly, the highly ionized O3, which is being ionized by the AGN. And what we started to find were these very, very fast blue-shifted outflows in the highly ionized species. So this is 300 kilometers per second, spread over 2 or 3 kiloparsecs. So these are quite significant winds. The other nice thing about this is because the hydrogen alpha is actually showing us the stars in the galaxy, we now have a truly spatial three-dimensional representation of this galaxy. So this is the blue-shifted gas, and we know it's coming out towards us. This is the disk that's rotating nicely. If that gas outflow was into the disk, it would have disturbed all the kinematics, and it hasn't. So we actually now have a rather nice three-dimensional pictures, which is not usual in astrophysics. We're always has projected pictures of the sky. And so the kinematics is very important. We now have the MUSE IFU, which is 27 IFUs on the VLT. That's kind of mind-boggling in terms of data rates. So we can do this for multiple galaxies in the sky, or we can actually map the kinematics of large nearby galaxies. We also have all of the kinematics for free in all of our ALMA data, and the same in the radio, we do this for neutral hydrogen. The results that we found from here were quite interesting. We found a very fast evolution of AGN already by a redshift of 0.05 that we weren't expecting. And we saw that in the dynamics, so this is a dynamical evolution rather than just a structural evolution. We saw no host-stellar mass evolution to redshift of 1. The evolution is all in the gas, so that tells us something about the accretion into the hosts. And we're now extending that study to higher redshift. And so you can keep all of these things in your mind, to bear in mind the fact that when we look at our LSST images, we just have photographs. We'll have very deep, beautiful, complex photographs, but we will not necessarily know how the components in those images are moving. And we won't have all of this rich information about the different traces until we add ancillary data across the electromagnetic spectrum. And as I say, this just shows some of the other optical cubes. This is KMOS on the VLT. And these kinds of outflows in galaxies are now thought to be ubiquitous. We don't know whether they're driven by star formation rate, stellar mass, or dynamical mass. But it's clear that this kind of feedback is very, very important for the evolution of the galaxies. And it may be that the deep imaging in LSST will tell us what the environmental effects are that are triggering these sorts of outflows. And in fact, the SKA Pathfinder ASCAP in Australia will gradually start to produce about 10,000 galaxy cubes in the nearby universe in hydrogen. And so that's a good question. Can the gaseous traces be hinted at by the structures that we see in the LSST imaging? We saw some very nice deep images yesterday and the effect of scattered light when you have bright sources in the field. This is a nearby interacting galaxy that we've been studying for some years. You can see here the DSS and the SDSS image. If you had the contrast, you would be able to see a little bit of diffuse emission up here. We found hydrogen in the system, shown here in the red, extending almost 100 kiloparsecs north and south of the system. And we found that back in 1995, and it took us nearly 15 years to find the optical counterparts. So this is a very deep 8-meter image on Subaru. This is the kind of thing that you might expect to see with LSST. Again, we probably can't see in this light level, but there's a very nice optical plume here, which actually matches the H1, which is quite difficult to explain dynamically. So it may be that we get lucky and the diffuse emission in SDSS, once we can get rid of our imaging artifacts, will actually give us a trace of the extended gas halos. And then of course we have the most luminous quasar systems, and these become a real challenge. My expertise is in local galaxies, where I'm used to being able to see the host galaxy and lots of detailed structure in it. When we go to the most luminous systems, of course, we're completely dominated by the AGN. So these just look like stellar point sources. You can't actually see the host galaxies in most of them. And this is what Carole has been working on with her group, and they've developed a very nice Bayesian Markov-chain Monte Carlo method for actually decomposing the spectra, just simple on-slit spectra, through these bright point sources. And what she's been able to do is actually extract the host galaxy light, which contributes only 10% of the light in the spectrum, and she's able to study all of the star formation in the host galaxy, which I think is very impressive, given we can't even see the hosts. So I think there is a challenge there for LSST. She's actually studied nearly 4,000 SDSS quasars, and so it's clear that the spectroscopic follow-up of the LSST imaging will be very, very important. And so if we move on to variability, this is something that's being studied by a number of the US teams, particularly in how we do this for large numbers of sources. And of course, AGN have always been, all sorts of sources have been selected on their colour. You can plot on a colour magnitude diagram, and you can try to figure out what the different kinds of point sources are. In this paper by Choi in 2014, they were trying to understand whether instead of plotting the light curves of objects, they could actually look at difference images. And you can just see here a collection of difference images taken at various different points in the light curve of a quasar. And this is a co-added template of the structure there. And what they found when they actually put X-ray data with this, and they used X-ray data to guide them so that they knew they had bona fide EAG, and they weren't just using the optical. And again, that's a cautionary message for the LSST era. And what they found was that genuine X-ray selected AGN point sources, and they studied the star formation there, and they did find that the fainter sources, which is coded here in G-band, so the darker is fainter, are down here. And in fact, it looks as though the fainter sources have shorter timescales. I think they're still looking at the semantics there, but it's actually a very tantalizing result. Similarly, the SDSS team, this is a sub-project in the SDSS4 EBOS work. This is a time domain spectral survey. And this again is a very nice precursor for LSST. And the idea is actually to do spectroscopic identification of over 200,000 luminous variable objects over an area of about 7,500 square degrees. And what they found with the pilot studies is that actually variability complements very nicely colour selection. They find additional redder quasars, and it actually mitigates some of the redshift biases. So again, this is important for the Photometric team for LSST. And in fact, they're also finding more higher redshift blazars and also broad absorption line quasars that we've just made colour selected samples. So it kind of smooths out the selection effect. And of course, we know that AGN vary in much shorter timescales than this gradual variability that you might look at in colour maps. And for many years, we've actually been looking at high energy triggers. It's easy when you get a high energy trigger because then you can trigger your optical follow-up. We'll have to learn in the LSST era, as we heard yesterday, how to code with 10 million transient sources a night. We might filter those down to a million, even if we get them down to 100,000, it will still be a real challenge to do follow-up with them. And we've been interested using our suite of robotic telescopes, particularly looking at high-energy flares. So we have things like Fermi-satellite integral SWIFT. If a high-energy flare from an AGN is discovered, we're able to follow those up. And this will be particularly important when CTA is built, because they will have a survey mode, but they will also find high-energy flares. And they're extreme particle acceleration. LSST, we can mine the data, but we might also want to use some triggering. And again, LSST itself can be a self-triggered follow-up. We know how to do this, so we've been doing this for gamma ray bursts for the last 10 years at least, in the era of rapid follow-up. These, of course, are very extreme objects. They're gone in seconds. They probe out to the highest redshift, the highest photometric, the confirmed GRB is out at redshift of 9.4. We do have the Sluse satellite, which is a very effective tool for finding these high-energy bursts. It gives us very accurate localizations that we can immediately follow up, either with the ultraviolet and X-ray telescopes on the satellite or from ground. And we now have over 1,000 gamma ray bursts that have been detected with the Burst Alert telescope. My group spent a decade building a program to actually follow up these gamma ray bursts in real time. So the goal is to be on within a minute of actually finding these triggers. And again, you can consider this to be a pilot project for the LSST era. We're not very intelligent in the middle of the night when we get a trigger on our mobile phones, and so we put much of the intelligence into the software. And we can now receive a trigger from actually anywhere. We can take it from neutrino detectors as well, but mainly from SWIFT. We actually trigger the telescope then takes observations, analyzes the data, looks for new objects, interprets their properties, and decides on the subsequent follow-up whether there should be colorimetry, spectroscopy, or multicolour imaging. And all of that is done without any human intervention. And that's my technology. And it does work. This is the first multicolour optical light curve that we made with the GRB back in 2005. And the Liverpool telescope began observing just 3 minutes after the gamma ray burst happened. And we've since got faster. We've now followed up over 230 GRBs. And as I say, we couldn't do this without the autonomous technology. This is just a real sky map that the GRB community uses so that you can find out whenever a source has gone off, it flashes red if it's a new source. The old sources are there in blue, and you can find all of the information by hovering your cursor over the source and anything that would find when you're actually uploading in real time. So again, all of this can be automated even more than it already is. So as I said about AGN variability in AGN so far has not been so prohibitive as GRBs, but because we can do GRBs, we can actually do AGN very quickly. We began a project a number of years ago when LM-87 went into outburst, and we actually detected a gamma ray flare with MAGIC. And we then started to use the same kind of technology that we use for the gamma ray bursts to follow up AGN high energy triggers. And what we also did is, because the robotic telescope can run in monitoring mode, once we triggered on the flare, we would just leave the AGN in the database. We won't telescope time for that. So So we actually have long-term monitoring of these things. And you can see the typical variability of the quasar here, anything from 14th down to 18th magnitude. And we do expect to find, obviously, the whole faint end of the luminosity function of LSST. Most importantly, we're combining it with high energy data and also the polarization properties, which gives you a fundamental handle on magnetic fields. Macarian 41 is a very famous AGN, so obviously with LSST you would know where to look. We have a phenomenal database of LSST. What was very nice about these data though was we actually ended up with a precursor of the polarization data that wasn't really reflected in any of the direct flux light curves. So in the high energy nothing happened until it went down. Not much happened in the optical either, apart from the polarization percentage. So we actually had a precursor. 60 days before that gamma ray went on. So it's clear that LSST, combined with other kinds of dimensions, if you like, if you want to put polarization spectroscopy dimensions, will actually help us to diagnose some of the physics here. And in fact, this is a paper that our student Helen has just had accepted, where she was able to do this for a very large sample of quasars and actually study the correlation between different kinds of quasars. So flat spectrum radio causes low, intermediate, and high spectral property quasars. So this is a very nice paper that you can look from the archive. And of course, it won't just be known accreting black holes that we'll find. The really big pioneering frontier for LSST, I think, will be actually tracing the quiescent black hole population. We know by detecting gravitational waves that there's potentially a whole population of invisible black holes out there. But we also have supermassive black holes at the centers of galaxies, which intermittently will devour material close by from the host galaxy. SWIFT has detected 2 of these tidal disruption events at high energies, so gamma ray and X-ray wavelengths, and they last for many, many weeks, and they're actually very easy to monitor once you find them. There have been a couple of optical tidal disruption events reported by pan-stars, and we are hoping that LSST will find multitudes of these. We think that there will be a technical challenge, so observationally it's not difficult to follow these things up. We actually had one that we literally followed up last week. This was a nearby galaxy, NGC 4708, and John Czerny and his team found that the nucleus had flared by electrical magnitudes. And he's running his ATLAS experiment, which is 2.5 meter telescopes, and these are monitoring the sky for near-Earth objects. And he happened to see the flare at the center of this galaxy, so he put out an astronomical telegram. We used the Liverpool telescope for follow-up. We did multicolour imaging, spectroscopy, and polarimetry. So even though it was only a 2-meter telescope, already you can see that we discovered a nice tidal tail that connects this galaxy to a small companion. You can imagine what that would look like with LSST. It has a small bulge, and if we just drop the contrast down, you can see into the nucleus. And we had high hopes that this would be a tidal disruption. We took spectroscopy right through the nucleus. This source was only up for 2 hours, so we hit it with everything. And we just missed the bright source that night. We went back the next night and discovered that it was actually a type 1a supernova pre-peak. So the supernova people were excited, tidal disruption event people were disappointed, but it's a very good example of the kind of thing that we'll be able to do with LSST. The interesting thing here, though, is the way the programs are set up, the reactive time programs. We now actually need to hand this onto the supernova community. So there's also a coordination across the community that's needed. There are the sort of political and logistical issues. It's not just technology that we're talking about here. And indeed, we're now entering a very exciting multi-messenger landscape that LSST will be an important component of. As I say, we have our robotic rapid response telescopes to follow up discoveries. We'll also have the square kilometre array and the Czerny telescope array, so that will cover the entire gamut of the electromagnetic spectrum, along with JWST and ultimately W first. And then, of course, we have our non-electromagnetic particle gravitational wave tracers. So I think there's much knowledge in the community about how to do transient science, how to do follow-up science, and how to coordinate. And I think that tapping into that and thinking back to LSST will be very important. So to conclude, I think AGN science, amongst other areas with LSST, will be very exciting. It will be challenging, and it will touch on many of the other working groups. We care about everything from the host galaxy right down to the nucleus and anything else in between. And variability and spectroscopy, and indeed other traces like polarimetry and multi-wavelengths, particularly high-resolution radio imaging, really helps us to diagnose the physics. And so there are two kinds of experiments. There are the statistical experiments that you'll do, and then there are the actual physics of objects. My particular interest is in fast transients, and fast is a matter of perception. If you speak to radio astronomers, my transients are slow, because they have things like fast radio bursts that are gone in 10 milliseconds. And if I speak to stellar astronomers, then my transients are fast, so it's all relative. We can do autonomous follow-up now. We really need to think about the filtering algorithms and these kind of science questions that we want to answer. And I think, a real take-home message for this audience is that, the future is very bright. And we also have a huge amount of resource within our community that if we can coordinate together, we can really put Europe at the heart of the leadership here. Thank you. We don't actually have to do the separate imaging module, we just go straight with the polarimetry. But in principle, we could have that detection mode in there if people were interested in discovering other kinds of objects. At the moment, we don't combine these things and doing the temporal properties of the polarization. But we had a number of challenges. It sounds almost trivial when you describe it, but as some of the people mentioned yesterday, you end up with artifacts on the side of the images, and the algorithm will go and think it's found an object at the edge. We had to crop, we had to match with catalogues. And then occasionally, very occasionally, we would have maybe 6 magnitude starring fields, and the GRE would be very close to it, and it's not further strong. But it comes back to us with that confidence number, and either a position and a brightness and a probability that the thing is real, or I haven't found something and therefore I'm going into this other meeting. It took us several years to prototype that with Monte Carlo simulations and actually really on the sky, because they primarily have no idea what these things would look like. So I think that it's a good test model for future farming and other things like time construction events. The beauty of doing gamma reverse is they are naked point sources. It does become much harder when you're starting to look at things against the bright background of the bulb in the galaxy. So that would just caution that that's a new challenge.
Okay, any more questions? Right, it's time to start again. So our next speaker is Bozena, and she's going to talk about photometric reverberation studies for LSST, starlight.
actually cosmology, we think that AGNs can be used also as a probe of the dark energy. The advantage of AGNs is that they cover a broad range of redshifts. You have nearby AGNs as well as distant quasars up to redshift 2, and a lot of quasars are at redshift, up to redshift 7, and a lot of quasars are at redshift 2. Now, okay. Well, quasars are more difficult than supernovae 1A because they are more complicated, but we have a lot of understanding how quasars work, and here you have the standard picture. You have a black hole, you have an accretion disk, and you have the broad line region here, and we can use that to construct the luminosity distance diagram. So quasars are not standard couples, of course, orders of magnitude difference between one object and another, but it does not matter as long as we know how to derive the absolute luminosity of a quasar. So for that we really have to understand how quasar works. It consists of an accretion disk surrounding the black hole, as we heard recently. So the continuum emission, and here you have a representative the spectrum of the quasar. Continuum emission comes from an accretion disk, mostly from from the part close to the black hole, while emission line comes from the broadline region, which is distant. So, accretion disk is strongly variable, emission is strongly variable, and broadline region responds with delay. The key statement is that this delay, or the size of the broadline region, is proportional to the absolute luminosity. So all you have to do is to measure the time delay between the line and continuum, and then you have the absolute value of the quasar luminosity, and that opens cosmological applications. So what you have to do is to understand this dependence between the delay and monochromatic luminosity. There are observational facts behind that as well as theory. Then you measure the time delay. Then you have the monochromatic luminosity of the quasar, and comparing with the observed luminosity of quasar, you have the luminosity distance, and independent you have redshift to the quasar, you have Hubble diagram. This is what you need. So there is some theory behind that which makes it relatively safe to extend this kind of delay luminosity relation to large redshifts. We developed such a theory to the observed path. It is based on a very simple statement known from stellar astrophysics. If you have the dust contribution to the atmosphere of an accretion disk or the star, you have immediately a strong wind. So in the case of an accretion disk in an AGN, here the temperature is high, here the temperature goes down, finally it crosses the sublimation temperature, and you have this kind of wind, and we understand this. This is the mechanism of the formation of the broadline region. This is not really a wind, this is a fake wind. I don't have time to explain that, but it's caused by irradiation and dust evaporation in this range. So if we know the dust temperature, we don't need any scaling based on nearby sources. We just know how to scale this relation, monochromatic flux, broadline region size. The dust temperature can actually be measured from the spectra. It should be about 1000 kelvins. So what we have to do is really to do a lot of measurements, and this was usually done using spectroscopy, and it was done for nearby AGNs very successfully. But now we have to do that, or we should think about doing that using LSST, and then we have colors and not spectroscopy, and it changes a lot. I will now show our pilot study of how we can do really that with LSST. So lines which are promising are 3 lines, H-beta, magnesium 2, and carbon 4, depends on the redshift. So we do the simulation. We simulate the quasar spectrum and quasar variability, and then we fold that with LSST responses to create colors. So our spectrum is quite advanced. I think it's not doing badly. We assume a power law. We took the equivalent width of all lines, taking just the average value calculated from Czerny catalog. So there are better sources, worse sources. We use ion pseudo-continuum in all wavelengths, and we take the starlight shape from our modeling. This is based on Sid Fernandez software, so it uses those templates. So we constructed here, you see just the starlight plus power law, and then we add also lines. And now we study just one quasar, basically located at redshift z=1, but of course, the situation will depend strongly on the redshift, because as you see here, the contribution of lines and starlight depends on channel and redshift, right? So if I now concentrate on quasar, which is located at redshift 1, well, the starlight contribution, I was too generous here with this contribution, is noticeable. H-beta is well visible in one of the channels. Magnesium 2 is not so well visible. Well, partially, but it's not optimized for that. So I modeled, variability using Timmer-Kennig algorithm. So I have 2 light curves, one with channel without strong contamination, and one with contamination. And only this contamination part is delayed, so it's difficult, actually. So then I repeat the exercise 100 times at random for the same values of parameters. And if I don't assume the starlight, H-beta contribution is at the level of 16% to one of the channels. And, well, the measured delay, the actual delay, it was 780 days expected. The recovered delay does not look so well. The problem is that for some measurements, I have 0 delay, and this is due to the red noise of the light curve. If I throw away those things, the recovered delay looks quite well. In the case of magnesium 2, the contribution is only 6% for that redshift. So I think it's almost a complete failure, right? Because only in about 20% of cases I recover the delay which was built into the scheme, and in most cases I have just 0 time delay due to the red noise in both channels. If I use starlight contribution, in the case of H-beta, this contribution drops, but basically I can still recover the delay. So this is certainly a technical problem of those 0 delays due to the red noise. This will be very important in reality. So this was just a pilot study, as I told you. We did that only for one quasar. We can repeat that for all quasars, for example, from Czerny catalog, because we know all the parameters for those quasars. We know how to model them. We are not yet part of the LSST collaboration, so we are not yet motivated. We need additional moral support to do that, right? And of course, the way how we measure the time delay can be improved. because for the moment we use chi-square method, which is better than cross correlation than CCF. On the other hand, we are using linear interpolation. We can use that one, random walk for that. I'm not sure that this will improve a lot. Maybe, maybe not. Thank you.
Okay.
Have you included in your template the Balmer pseudo continuum consisting of the Balmer continuum and the high order excitation line?
Not yet. Not yet. I know how to do it. I'm not sure what kind of delay I should assume in that case. Probably it will go with continuum, but it may also come from the broadband region. So then I would have to decide what kind of delay built into the model for test. Perhaps part of the continuum comes from the broadband region, part is closer region.
Exactly in your template in the
Yeah.
maximum.
Yeah. Yeah.
Next to the
Yeah. I have a template for Balmer continuum independently, but not built into the model.
Together with the high order Balmer.
Yeah.
You said that you modeled the iron lines in magnesium, yes?
In all that.
All that.
Yes.
Which,
Yeah, optical as well.
which template did you use?
I use combined template, so it's mostly theoretical template actually taken from, I'm not putting remembering references, I can give them to you later on. And where those those theoretical templates were not working, I took some observational, so it's a combination. But it worked for our quasars. We do monitoring with the SALT telescope, and we constructed this template for that purpose.
We should move on. Next time, Bozena, yeah. Our next talk is by Dominique Sluse, and he will tell us about imprints of the AGN structure on time delay line results.
So hello everybody. I will explain you today how we plan to be able to, how we want to do one-dimensional tomography of AGN using two telescopes. So on one side LSST, and on the other hand gravitational lensing as a telescope. So basically 1/500 AGNs is can be gravitationally lensed due to the presence on the line of sight of the foreground galaxy. So when an AGN is in the background of the galaxy, the potential of the main lensing galaxy informs the space-time, and an observer can see multiple images of this background AGN as shown on this picture. So here you have an image of a lens AGN. You see four lens images of this AGN and of the whole galaxy. Here, the white parts here are the formed images of the whole galaxy. And as you can see, the brightness of the different lens images is different because there is a magnification effect associated to gravitational lensing. And the center you see the lensing galaxy, and the typical separation is of the order of 3 parsec. So this is a strong gravitational lensing effect. But on top of this effect, there is the beam from each of the light of the strongly dense images is crossing a different part of the lensing galaxy. And so the modularity of the lensing potential due to the stars in the lensing galaxy. The stars in the lensing galaxy act as secondary gravitational lenses. So they also reflect the light rays from the background image and produce micro images on scales of micro arc seconds, because the stars are much less massive than the main lensing galaxy. So these micro images, so each of these images is formed of many micro images that are just unresolved. But everything is moving, the lensing galaxy is moving with respect to the poles and with respect to halves, and the stars in the lensing galaxy are moving as well, and so the effect is dynamic. And so what we see at the end is only a fluctuation of the flux of the lens image due to these micro lenses. So these micro lenses produce a fluctuation of the flux of the macro image that can be followed with time over a long period. So what part of AGN is affected by this micro lenses? So these micro lenses really act as a small magnifying glass that magnify the source on scales of the order of the Einstein radius of the micro lens, which means of the order of 10 to the minus 2 parsec for stellar mass like stars. So the region, AGN spectrum is made of basically you have the optical, you have a polar continuum, and on top of it you have these broad lines and narrow lines. So the polar continuum is emitted by the central accretion disk, and which has just this size of the order of 10 to the minus 2 parsec. It means that basically this region is the one that will be the most affected by microlensing, while regions that are bigger, like the broad lines, will be less affected, and the narrow lines or the torus are basically unaffected by this microlensing effect. So we can take advantage of these differential effects to really probe the structure of the AGN. And in fact, the most interesting is really going to the structure of the accretion disk, because there we do see differential effect within the disk. And this is shown by this slide. So this slide is a simulation of microlensing of this multicolor source. So this multicolor source is basically an accretion disk at different, seen at different wavelength from the U band to the Y band for quasar activity, and it's a temperature profile which follows standard accretion disk model, Shackleton-Meyer standard accretion disk model. And on the background here, you have what we call a microlensing map, which is a simulation of the effect of microlensing. I will not enter into the details, but basically these maps encode the amplitude of microlensing in the source plane. And the white regions correspond to the regions where microlensing produce a high magnification, and the dark region where microlensing produce demagnification. And if you move the source through this map, you basically simulate microlensing event. So on the right hand side, you have the simulation of the variation of the microlensing light curve for the various source sizes, so from U band to Y band. So what you do see is that the amplitude of variation is much stronger in the violet here, for the compact U band emission, than for the wettest source size in Y band, where you do see that the amplitude is basically twice smaller. So this is for a source size of 1 light day at 1,126 ampere, and this is the same thing for a source size 10 times smaller. But you do see that this the impact on the microlens, the amplitude of microlensing, microlensing light curve is significantly different for a 10 times smaller light curve. And you do see here the type of variation. The chromaticity is less stronger, but it's there. So this is really a way to measure the size of the accretion disk, and by studying the chromatic changes, you also study the temperature profile of the disk. And this has been done. This is not science fiction. This is an example of this, of the use of microlensing, chromatic study of the chromatic changes observed in the Einstein cross-lens quasar. So it's a quadruply lens quasar. In that case, we obtained spectroscopic data to remove the borderline emission, but it's basically at the end we end up with getting equivalent to multiband data from the blue to the red, and you see that the amplitude of microlensing is stronger in the blue than in the red. And by means of simulations, microlensing simulations, where you basically include in your Bayesian simulation, where you change all the possible parameters, source plane parameters, so the source size, mostly the source size, and parameters associated to the noisance parameter, and you end up with, by trying to end up with getting a family of light curves that do reproduce the observed light curve. And from this, you derive a most likely source size, a distribution of source sizes for your source. Okay, and so this way we ended up with a temperature profile with a most likely source size for these 6 bands, and the source temperature profile that is consistent with Czerny. So the status is this has been done with less good quality light curves for basically 10, 20 AGNs. And systematically, people have found that the source size is bigger than the Czerny accretion disk source size. This has been recently confirmed from reverberation mapping of the accretion disk. And on the other hand, we also found in the system, thanks to microlensing, evidence for extended emission, not coming from the accretion disk, but from a region between the accretion disk and the borderline, which is probably some scattered emission line. But this is not enough to explain this oversize of the disk. And so in the LSST era, we will have basically an order of magnitude more lens AGN than what we have now. And basically 2 orders of magnitude, a possibility to study 2 orders of magnitude more AGN, lens AGN that is possible now. So it's really a huge increase. And here I will give you a glimpse of what will be, what could be kind of LSST-like light curves. So whether the cosmography monitoring program, which was a monitoring program of 10 lens, of 20 lens AGN with monitor plus telescope for a period of not 4 years, but 10 years. So you have basically the cadence once every 4 days, 10 days, and and so you do see intrinsic variations of the different lens images. So ABCD, ABC, and HD. You do see variations that are correlated between lens images, and variations that are neglected because of the time delay. But if you correct for this time delay and do the difference between light curves, you basically get only the extrinsic signal due to microlensing. And doing this, we found, so this is the intrinsic light curve of the A of the D and then the difference. And this difference is pretty surprising, in fact, because originally we were expecting something varying relatively smoothly over time. And what we do see is something which does vary less smoothly than what was expected from the standard one. So this is a very interesting result. and which still needs to be fully understood. But it's a kind of new discovery potential of LSST as well, because this is seen for several objects, and with LSST we may expect to see it for even many more. And understanding this is really one of the next challenges of the microlensing studies. So we see this fast microlensing variation. One possible explanation of this could be just that we have to change the accretion disparity. And in the modules, this model could be a possibility to go because it both explains a larger source size and may produce also quick variation in the light curves, as we do see in the system. It has not been tested yet on those light curves, so I cannot say this is the explanation, because in fact there is possibilities such as the contamination from the borderline of usually we observe in both filters. So we have not only flux from the continuum but also flux from the border emission lines that may produce small fluctuation as well. Well, with the LSST we'll have multiple colors, so we can disentangle between those, because the contamination by the borderline is different with the different bands. Other possibility is we have an imprint of this extended continuum emission. We don't know if it does exist in other systems, but I think this is an important science question also to investigate how much, and finally I want to just point out that there was simulation that shown that it would be possible during high magnification events to also see possibly signature of the spin of the black hole. The microlensing light of high magnification event would change a bit depending on the spin of the black hole. So yeah, I will finish here. I think my conclusions. I've been a bit too long. I'm sorry, and looking forward for LSST to investigate this a bit more.
Sorry, I did not understand exactly. So have you modeled the size of an accretion disk to account the scattered radiation? Or it's just that you are convinced that scattering doesn't happen?
For in one case,
Well, the general case, because this polarization measurements show that we have scattering.
yeah, we have scattering. But the scattering has not been included in the model of microlensing for now, and because in general it was thought to be small amounts, but in practice, I mean, it was not so small. Yeah.
So you showed the color accretion with the different dimension in colors. It means that you use different bands, different dimensions in this for different bands. Yeah. Okay. Not use set, because we expect that we have distribution of the temperature across the disk. Not you calculate set or spectral energy distribution or only different dimensions.
Here we consider, for the simulation, we consider different, the mean dimension of the disk at the given.
Okay, thank Dominique. So our next talk is by Luka, and he will be telling us about detecting sub-parsec supermassive binary black holes. So, okay, I will try to give some ideas to detect sub-parsec have very coarse binaries that they have cycle binary application discount for the possible black holes. So, in last several years, we have several papers. You can see here is I think only 10% papers that they are dealing with black hole binaries. And first of all, trying to use SDSS databases and line shapes. And second is to find periodicity with low line like Earth and continuum. First of all, it is a question if you have some complex line like this, where you have two peaks. If the line is treated in some binary line division, and then there is a problem because we have different alternatives as emission from this, bipolar outflows or something like. And also we have for the asymmetry line profile, expecting that one component gets more line division, moving very fast around mass component. So there is some models that we can model, for example, full line divisions, and as you can see, the line profiles can be very different. It depends from the phase of the, it depends from the phase of the radiation and also plane of angle plane of radiation. You can have wide symmetric line profiles and also have big line profiles. What is with the most important information and the part of spectroscopy LSST will be several bands. So in that case, we have good photometric observation. We can simply try to find some periodicity in the line curves. As you can see here, these quasar E, 8, and 1. And so, for example, in this case, we can find periodicity that is 1,200 days. This periodicity can be produced by Mohr or two black holes that we have in any case primary and secondary black holes, and Imprints secondary black holes can be in the gas reservoir and have annotation list. Here is another case where we have periodicity light curves. It is reaching 30.2. And as you can see, we can produce light curve using model of binaries, and this is what's here in this paper. About periodicity, it depends first of all from the distance of holes, masses of black holes, and the distance between two black holes. So for LSST, because we will get observation of black hole and small period of time, then we can look for such kind of binaries that they are very close to show there, and they have periodicity between several days to 10 days or orbits are lasting such period. Model we use as usual in the case of AGNs. We use Czerny accretion disk and taking that active temperature depending from the accretion masses and also from inner part So, okay. Also, the model, this is a case of 1 year periodicity, and calculated is solid line here, and those are very good white noise, and we try, we have relatively good forward observation, relatively good forward points through the 4 periods, and as you can see, if we use 100% of the points from the period, we obtain exactly the period of the orbiting of the black hole, massive black hole, black holes. If we taking here is 80%, we still have period from starlight, and also 60% of points is covered of the region. We have also very significant bit here, but if we are going below 50%, then we cannot see periodicity like this. Also, we have several problems. You can see some example if you have observation in some period of year, then you cannot find a very good periodicity, and what we can expect is black hole binaries that we have outbursts that will also affect the light curves. So this is conclusion. Currently this is in progress. We expect periodical oscillation is recommended solution. It is a question, can we observe stellar mass binary black holes of the question from future work? And also why not in future LSST might be point out some objects that can be very interesting for light observations as well. Thank you.
Any questions for Luka?
Can you also model spiral waves? Because you know that this accretionist has this self-gravitational instability, so spiral waves are also expected. And then such a spiral wave is a rigid structure, so it's not locally Keplerian and maybe a different signature, somewhat.
It's a good question, and also everyone from my group is on this problem, and they have some model that can explain also through black holes that they have spirals, and then the profile can be, line profile is very interesting. It's first some example similar as Mohr, 122B, and also some effects can be seen with the continuity. But how to say, we are working on more.
Okay, more questions? All right, it's time to move ahead. Our final talk is by John Mohr, and he will tell us about synergies between LSST and Imprints.
here's I guess just a nice, a few pictures of a mock eROSITA. You can see that eROSITA consists of basically 7 mirror modules, 7 sets of CCD detectors that are advanced versions of the detectors that are used on XMM. Here, next slide is actual flight hardware. Here's one of the cameras, one of the CCD cameras. Here's where the cameras are bolted on to the eROSITA main structure, and here are 4 of the 7 mirror modules already integrated. So this system, these 7 X-ray telescopes are co-aligned. They're all looking at the same part of the sky as the entire SRG rotates at L2. It sees, basically eROSITA sees a field of view which has a 1 degree diameter. And the survey angular resolution, the pointed angular resolution is about 15 arc seconds for these mirror modules, but averaged over the field is 25 arc seconds. So it'll be similar to the angular resolution from the pointed ROSAT PSPC observations. Here's just a comparison of the graphs. So eROSITA with the 7 mirror modules here as a function of energy compared to ROSAT here and compared to XMM. So it's a far more powerful survey instrument than has ever been available before. And relative to ROSAT, it reaches out into the high energies that simply haven't been explored yet on a pulse sky basis. Here in just, let's see, pulling some results from a science white paper from early 2012, which you can find here. You can see that, well, here's a little picture that helps you understand this. This is, because it's basically rotating through the ecliptic poles, you get very deep observations of poles, shallower in the middle. Characteristic around here is about 1.6 kiloseconds or so. And so that translates into a few hundred-degree survey that's quite deep, and all sky survey that is, significantly shallower. Characteristics for finding AGN would be over the whole sky something like 10 to the minus 14. There are a variety of other surveys. For clusters, which is the prime size driver, I'll say more about that in a second. We're looking at a few 10 to the minus 14. Clusters are the primary size drivers. I don't have time to talk about that. Here's just an example of the growth rate of structure parameter versus sigma 8 from a recent analysis from my group of the South Pole Telescope cluster sample, about 300 SC selected clusters. You can see the cluster constraints here are in comparison to long C and B constraints. So you can see that clusters are very good tools for studying the growth rate of structure if you can measure the redshifts and if you can measure their masses, and that's where LSST comes in. Here's just a nice plot showing the redshift distribution. So there's sort of 2 points to this figure. One is that the redshift distribution depends on the masses of the systems, and so I would focus your attention on this sort of region here, just the systems that are above 10 to the 14 solar masses, the sort of region where we have good confidence that we can understand the clusters. There will be a huge sample of groups in addition to that, but the clusters themselves are about 50,000 to 100,000. And this is a figure that you can follow here. The second point of this slide is just to kind of lay out different surveys that have been made in the X-ray, the SC, unfortunately, Quasar's depth only gets us out to a redshift of about 0.5. The regions that aren't colored here include Atlas, which also does a shallow survey, and DPALS that goes to redshift of about 0.8. So we'll be able to do good science with this patchwork of surveys, but with LSST it would be quite different. We would basically have complete contiguous coverage if the extension to a declination of plus 30 is accepted. That would take us up all the way to here. You can see just from this figure that this is the south celestial pole. So the western galactic sky is about 2/3 in the south celestial hemisphere and about 1/3 in the north celestial hemisphere. So LSST again is just a very good match. We can do optical confirmation of all the sources. There are about 1,000 galaxy clusters expected at redshifts greater than 1. We'll be pushing DES to do follow-up of those sources, but LSST we think shouldn't be a problem. The weak lensing mass constraints in comparison to DES, where we're currently getting 4 to 6 useful galaxies per square arc minute in our weak lensing analyses, LSST is expecting to get a factor of 10 more, so just a dramatic, much larger amount of information available. On the Asian side, time variability enabled by the LSST survey, as we've heard in several talks now, would be helpful. So then just the summary is that eROSITA will open some new window to the hot universe, launch and 4-year survey that follows starting 2018 is relatively well timed with LSST. LSST comes a little bit late. This survey will be 30 times cheaper than the eROSITA All-Sky survey, half arc minute angular resolution, CCD detectors that include energy effective area out to 10 keV. So that's a big step forward in the X-ray world. And then the synergies that I would see include cluster studies of cosmology. That's what my group's interested in. Optical confirmation, photosees, weak lensing, shear, and magnification constraints and cluster masses are crucial. And the LSST data set will take us way beyond the other patchwork of surveys, including DS that I mentioned. There's the environmental dependence of galaxy populations. There were some talks on this related to this yesterday. Basically, the SED fitting available from the LSST data set will be excellent for that. Evolution of X-ray emitting black hole populations, clearly broad interest within LSST. Also in that, optical confirmation, photosees with the 6 bands, you can do relatively well, and weak lensing studies of these systems too. And presumably, this will require some kind of collaboration agreement between LSST and eROSITA. Okay, so that's.
Any questions, Joe?
So LSST will have its camera ready, I think 2018 is its test camera. Will those data be useful for us?
Yeah, the 2019 or so, the beginning of commissioning, I would imagine so.